For the last 100 years, physical machines were built entirely blind. On assembly lines like this one, metal stamped metal in a repeating, unyielding loop. The instructions were hard-coded, and the equipment followed them without any awareness of its physical environment. Mechanical engineering relied on static tolerances. A static tolerance is a rigid, mathematical allowance for physical variation in a manufactured part. But as these gears spin, friction slowly shaves down the metal. If a cog wears down by just 0.2 millimeters, the machine does not know. It continues forcing its original, hard-coded parameters against the failing metal until the friction causes a catastrophic physical breakdown. For a century, engineering was defined by rigid rules that could not adapt to physical reality. These systems had a built-in expiration date, the moment their physical state deviated from their static code. That era of blind mechanics is ending. We are moving toward a data-driven model where adaptation happens at the hardware level. This relies on VLA models, vision language action systems, acting as the eyes and brain of edge hardware. Now, a machine sees its own degradation. When it registers wear and tear, it dynamically adjusts its own torque and speed in real time to compensate for friction. We have moved from static tolerances to hardware that actively perceives and adjusts to physical reality. The machine is no longer a set of gears, it is a self-correcting loop. This logic isn't limited to robotics. The transition from rule-based to data-driven is the new blueprint for all cognitive work. Most people still treat large language models, or LLMs, like a blind 1950s machine. They give the AI a single massive command and expect a perfect result. This results in AI slop, generic, low-signal content that lacks specific insight. The solution is prompt chaining. You break a complex project into a step-by-step assembly line, where each stage is a separate prompt. Chaining lets you verify Step 1's output before it feeds into Step 2, catching errors like a robotic sensor before total failure. This process replaces polished, generic AI writing with high signal truth. It forces the model to work with messy, real-world human data, rather than just repeating its training patterns. Without these multi-step loops, an AI tool is as blind and prone to breakdown as a gear grinding against a 0.2 millimeter deviation. To manage this system, the human user must act as the sensor. You are the one calibrating the AI's output against the friction of reality. We use a 5-point depth check for this. The first step is a confidence score. If a claim or metric in your output rates below 7 out of 10 for accuracy, you delete it or manually find a verified source. Second, you perform a specificity audit. If a paragraph lacks at least 3 concrete, quantitative data points, it hasn't earned its place in the draft. Finally, apply the so what test. If the information doesn't trigger a direct, measurable action for the reader, it is cut. These checks transform you from a passive recipient of AI outputs into an active architect of high-value intelligence. There is a paradox here. We are building these highly adaptive, self-correcting systems while running our own lives on rigid, failing mental hardware. AI has critical blind spots. It lacks real-world common sense and an understanding of the strict regulatory boundaries found in industries like finance or healthcare. We manage these blind spots with the ACT checklist: ask, check, and tell. Ask if the task is safe for AI, check every fact for subtle hallucinations, and tell your stakeholders exactly how the AI was used. This also requires sanitization filters. Before you upload data, you swap real names and project titles for generic placeholders. This prevents sensitive information from entering public models and reduces the risk of bias. Bypassing these safety protocols is the operational equivalent of removing the safety guards from an industrial machine. You are inviting a catastrophic failure. The builder is part of the system too. The same logic of friction that applies to a mechanical gear or a digital prompt applies to the person managing them. If you ignore the friction in your own life, neglecting your physical health, internalizing relationship stress, or running a business model spread too thin, you are operating on a static tolerance. You are running a machine that has no sensor for its own degradation. Unaddressed friction causes systems to fail. If the builder refuses to adopt the adaptive feedback loops they build for their machines, they will burn out long before the technology ever launches. Stop building rigid hardware and stop accepting uncalibrated feedback loops in your own life. build systems that actually adapt to the reality of the friction.